Okay. Today I want to compare the secant method and the Newton's method first, and then turn to section 4. Here, this formula is Newton's method, and this is the secant method. A big difference between these two methods is one is practical method, the other one is non-practical. But today, I want to compare them only in terms of computational cost and in terms of convergence rate. Now let me make two tables. This table is for the Newton's method. This is a Newton's method. In Newton's method, one iteration, we need to evaluate two function values, f of x, f of xk. We need to evaluate derivative at x of k, two function values. This is a function evaluation. Each step. The convergence rate for the Newton's method is order 2. That means that error in k+1 step roughly is some constant times error in the previous step square. In general, Newton's method is order 2 method. How about secant method? Each step, how many function evaluation we need to perform? Evaluation. Hey, when k is 0, when k is 1, not 0. When k is 1, plugging 1 in k, then we need to evaluate function value at x1 and function value at x0. So we need to evaluate two function values. Which two? Yeah, f x1 and f x0. When k is 2, we need to evaluate k is 2. So function value at x2 and function value at x1. But function value at x1, we got it from the previous step. So actually, when k is 2, we only need to evaluate one function value. When k is 3, we need to evaluate function value at x3, function value at x2. But function value at x2, we got it from the previous step. So actually, we only need to evaluate one function value. So for the secant method, each step except the initial step, we only evaluate one function value, f xk. The convergence rate in general, it is a 1.62 worse than Newton's method. In other words, ek plus 1 roughly is some constant times EK. The power is 1.62 roughly. So Newton's method is order 2 method. Secant method is order 1.62. So from the only in terms of convergence rate, Newton's method is better than the secant method. However, because one iteration of the secant method evaluate only one function value. So if we combine if we view 2 steps of secant method, then 2 steps of secant method in terms of computational cost, secant method is comparable to Newton's method. Combine 2 steps, view 2 steps of secant method as 1 step, then we have computational cost the same, also 2 function values. But how about convergence rate? Okay, EK plus 2. Convergence rate for the secant method roughly is constant times EK 1.62. K plus 1, 1.62. But this is a roughly C. EK plus 1 roughly is C times EK 1.62, then 1.62. So this is equal to C distribute the power. Then it is C to 1 plus C to 1.62. So 2.62 times EK 1.62 times 1.62. It is 2.6244. If I view 2 steps, combine 2 steps as 1 step, then secant method has the same computational cost with Newton's method, but the order is 2.62, much better than Newton's method. So which method is better? Of course, secant's method, much faster than Newton's method. And also secant's method is practical. It doesn't need derivative. So the conclusion is, which one is better? Of course, secant method is better. It's better. So this is what I want to say about topic 1. Now, topic 2. Section 3.4. Fixed points and the functional iteration. Yeah. Topic 2. This is section 3.4. In this section, we still solve a single equation. Okay? Single equation. All right, now let me introduce some definitions. Number 1. What is a functional iteration? Yeah, functional iteration. Functional iteration. An iteration defined by the equation, the following equation. Xk plus 1 is equal to f some function of xk, where k from 0, 1, 2, and so on. It's called a functional iteration. A functional iteration, okay, where capital F is some function. So a functional iteration definition is simple, means this equation. Definition number 2. Definition number 2. If capital F, the function value at some point S is equal to S, then we call that S, this number, it is on x-axis, is a visit point of the function capital F. Definition number 3. A function, sometimes we call a function a mapping. Function takes some value to another value. We also say that this mapping maps x to y, or a mapping, same meaning. Say capital F is said to be contractive on some set S. Yeah, this function is contractive on the set S. What it means? That means if you can find there are xx, a number, the number greater than or equal to 0, but less than 1, such that function value at x minus function value at y in absolute value. Yeah, we often use absolute value, okay, in error analysis. Less than or equal to lambda times x minus y in absolute value. What is x and y? X and y, arbitrary points in S, any point in S. For any x and y from S, we have this inequality. Then we say that function f is contractive on the set S. Yeah, mathematics definition is most important. Okay, always refer to the definition. Definition explains clearly explains the concepts. And let me show you examples about function iteration. There are many examples. Say for example, examples. Take a look. Examples. Example 1. A. The Newton's method is a functional iteration method. Newton's method. Recall that the formula for Newton's method is xk plus 1 is xk minus f xk. Derivative xk. This is functional iteration. What is functional iteration? Definition is, yeah, an iteration of this form is functional iteration. That is a functional iteration with capital A, capital F. What is capital F? Yeah, capital F is this. How about B? How about the Stephenson method? I mentioned this method in one previous class. Stephenson method. The formula for Stephenson method is xk plus 1 is xk minus xk function value square, then over function value and xk plus f of xk minus f of xk. Yeah. This is a functional iteration. Is a functional iteration. What is the associate capital F? The capital F is this: x minus f x squared, then over f x plus f of x minus f of x. There are many examples. How about an example about an iteration is not a functional iteration? The secant method is not. Yeah. Let's see. The secant method. A secant method, the formula is xk plus 1 is xk minus function value xk minus xk minus 1, then over f of xk minus f k minus 1. Yeah. Now this time, this is not a functional iteration. A functional iteration is this. The right side, only xk appears, but here the right hand side of this equation also involves xk minus 1. So this is not a functional iteration. Okay, now section 3.4 only focus on an iteration of this form. Okay, the first theorem is very important theorem. Okay, theorem about a functional iteration theorem. Okay. This theorem is named contractive mapping. A mapping is a function theorem. This theorem says that let S be a closed subset of the x-axis or of the real line. Closed subset, say for example, a closed interval. Yeah. A closed interval. Say A, B. This is a closed subset of the real line. In other example, say 1, 2, 3, 4, 5. These 5 numbers together. The set is a closed subset of the real line. Okay. Usually, here S means a closed interval. Let S be a closed subset of the real line. Okay, if function f, capital F, is contractive. The meaning of contractive is in the definition above. It's a contractive mapping. This mapping maps as this subset into the subset itself. Okay. Now conclusion. Then capital F has a unique one and only one visit point in the subset. Okay. This is a conclusion one. Second conclusion. Furthermore, moreover, okay, this visit point is the limit of every sequence obtained by the functional iteration, by this. Okay. Every sequence, that means that when x0 initial points are different, then we have different sequences. But no matter how you choose x0, this iteration xk will converge to this unique visit point. Yeah, the visit point is the limit of every sequence obtained by the functional iteration with an arbitrary starting point x0. Of course, x0 is in the set S. In the set S. I'm not going to give a detail of the proof of this theorem. Let me just outline the proof. Okay, proof. Just outline proof. Okay. Arbitrarily pick a point. Okay. Arbitrarily pick a point. Okay. Pick a point. Okay. Then we have a sequence. We have a sequence by this equation. By this equation, we have a sequence. The sequence is x0, x1, x2, x3, and so on. Because f is contractive, we can show that the sequence, let me use this notation xn, okay? The sequence is a Cauchy sequence, a concept from functional analysis. What is a Cauchy sequence? Take a review, okay? For any epsilon, no matter how small, we can find that this notation means there is a capital N such that, colon means such that x m minus xn in absolute value less than epsilon whenever m n greater than this capital N. If a sequence has this property, then the sequence is called a Cauchy sequence. Cauchy sequence. Because function f is contractive, we can show that for arbitrary x0, the resulting sequence is a Cauchy sequence. But Cauchy sequence must have a limit. This is an important property about a Cauchy sequence. So xn, this sequence is a Cauchy sequence. So conclusion, when n approaches infinity, xn will approach some point s. Here, we assume the set is a closed set, and also the mapping F maps S into S. That means that in this sequence, each point is in S. Okay, starting point is in S. Because capital F maps the set S into itself. So x1 is also in S. Every number in the sequence is in S. Now the sequence converges to some point S. And S is closed. So therefore, this point is S. This limit is in the set S. Now, this S, it can be seen. This is a fixed point of capital F. So we have a fixed point. Now, how to prove unique? Now, unique is very easy to prove. Suppose S1, S2 be two fixed points. Now S1 and S2 must be equal. How? S1 minus S2 in absolute value, we often use absolute value. They are fixed points. By definition, this is a f of S1 minus f of S2 in absolute value. But the function f is contractive. So less than or equal to number lambda contractive. Here definition is here. No definition. Contractive. Here. Contractive definition. Lambda less than 1. Okay. All right. S minus S2. But because lambda is less than 1, S1, S2 satisfy this inequality. The only possibility is S1, S2 are equal. if S1, S2 not equal, a non-zero number not greater than some number less than 0 times the non-zero number itself. Impossible. So this implies that S1 minus S2 must be 0. So this implies that S1 is equal to S2. So the physics point is unique. Okay, unique. Okay. Now here, the part here, I show that arbitrarily pick upon x0 from S. The resulting sequence has a limit. The limit is a fixed point. Now, the fixed point is unique. So this proof, this theorem is proved. Okay. Yeah, this is an important theorem about functional iteration. Functional iteration. Right, let me show you one example about this theorem. An example about this theorem. Okay. And example. Okay. Use the theorem to show that the following sequence has a limit. The sequence is initially negative 15. Then k plus 1 is equal to 3 minus 1/2 absolute value xk. Okay. This is when k greater than or equal to 0. Okay. Yeah. So that the question is the sequence has a limit. Actually, this sequence is resulted from a functional iteration. The function is, okay, look at the second equation here. The function is easy to see that the function is equal to 3 minus 1 over 2 x. Now, I want to use the theorem to show that this sequence has a limit. Look at the condition of the theorem. Okay, S is a closed set. Okay, let me in the theorem. Let me set S be the whole number line. The whole number line, of course, is a subset of the line itself and also is closed. Second condition, capital F is contractive and mapping from S into S. Of course, map this function of course maps the real line into the real line. No problem. Okay. Now the problem is how to solve. This function is a contractive function. Now contractive. Let me solve. Okay. The definition always go back to the definition. Definition is here. What is contractive means? A function is said to be contractive on a set if we can find a number less than 1 so that this inequality is true for any xy from the set S. Okay. Now the set is the whole real line. Okay. Now arbitrarily from the whole real line x and y, pick 2 points. Arbitrarily pick 2 points. Calculate the function. Then I get 3 minus 1/2 absolute value of x. Yeah. Then minus plug in y in x. 3 minus 1/2 y absolute value. Now simplify, cancel the number 3. And then take out 1/2. So 1/2 absolute value of y minus absolute value of x. But this is less than or equal to 1/2 x y minus x. Y minus x. Okay. Y x here without absolute value. How to see this inequality? You can have a check by picking some values for x and y to see whether or not this inequality is true. Actually, this is true for any x and any y. So therefore, I have found a number less than 1, so that this inequality is true for any x and y. F is a contractive function. So f is contractive on R. Okay, now I can apply the theorem now. Okay. Then conclusion, the theorem. Conclusion, okay, for any x0, the resulting sequence of this function iteration has a limit. The limit is the fixed point. Okay. So therefore, conclusion. So therefore, here, let me write solution. Conclusion. The sequence is convergent. Right? The sequence converge to some number. The number is the fixed point of this function. Okay, convergent. Say suppose that n approaches k approaches infinity. Then the limit is s, k approaches infinity. Now I want to determine s. How to determine s from this equation? Okay. From xk plus 1 is equal to 3 minus 1. Okay. I want to determine s. Let k go to infinity. Then the left side will approach s. The right side will approach this number. Okay. So s is equal to 3 minus 1/2 s. Now, divide this equation into 3 cases. First case, s greater than 0. See whether or not we can find a number satisfy this equation. Second case, set s less than 0 and see whether or not we can find a number satisfy this equation. Now the third case, s is 0, but clearly s is 0, not satisfy this equation. So after we consider 3 cases, we conclude that the unique fixed point is 2. Yeah, actually the sequence approaches 2. Yeah. This is the second topic. Now, third topic, very powerful theorem. Okay. Third topic. given a functional iteration, how to determine its convergence rate? Yeah, convergence rate of functional iteration. This theorem very useful, very useful. Yeah, we are often asked to tell the convergence rate about Newton's method, about Stephenson's method, okay, under certain conditions. It turns out that if we use the result in this topic, very easy to determine the convergence rate. Okay, much simplify the derivation. Okay, now topic 3. Topic number 3. Convergence rate of SK plus 1 is equal to capital F SK. Okay. A theorem. Assume that, okay, A function F is in this set here is Q. Hello. This notation means capital F is defined on the whole view line. And also function F has derivatives from order 1 to order Q. And also all the derivatives are continuous. Okay. This is what this notation means. Here, B. Okay, first, let me make a remark. In this theorem, we don't assume F is conjective. Yeah, we don't assume F is conjective. So this theorem is not related to the previous theorem. No relation, okay? No relation, yeah. Second condition is capital F has fixed point. Has a fixed point, say S in R. C and the fixed point S, we have a derivative of capital F at S is 0. Second derivative at S is 0. Third derivative at S is 0 until take derivative Q minus 1 times at S, still 0. But F, take derivative Q times at 0, non-zero. Okay. Okay. Now, condition D. Okay. The sequence. Which sequence? Yeah, the sequence. Yeah. Obtained by this formula has the limit. Yeah, I assume the sequence obtained by this equation has the limit S. Has the limit, okay? xk. Now k approaches infinity. Is S, okay, is S. Because we don't assume capital F is contractive, okay. So log guarantee each sequence from the functional iteration has a limit, log guarantee. So here I have to assume the sequence has a limit, and the limit is a fixed point. Okay, now I can tell how fast this convergence is. Okay, then the conclusion is how fast xk now is approaching S. How fast? Is fast. K to infinity. Okay, xk plus 1 minus S over minus S to Q, the power is Q, is 1 over Q factorial, absolute value derivative of capital F Q times S. But from this condition, this is a non-zero number. That means that this sequence, okay, what I can say that is this sequence, not this method. Okay? This sequence is converging to S. How fast? So fast. All the Q. Okay. Now conclusion. In other words, the convergence rate, okay, of the sequence, not this method, okay. This method for some x0, the sequence may not be convergent, okay. The sequence, the convergence rate of the sequence is of order Q, in other words. How to prove this theorem? It turns out that by Taylor's theorem, the proof is easy, but I present the proof in the next class, not today.